of Frontiers of Science Award. Its title is The Modules and the Singularities. Let's welcome.
All right. Thanks for the introduction and the invitation. I'm honored to present our joint result here. This project is joint with Professor Nero Budu, Robin Vadavir, and Penjo. Okay, so it is about the D module as singularities. So first, let's look at some motivations. So the first motivation is from arithmetic perspectives. So suppose we are given coefficient with integral a polynomial with integral coefficients, and we are going to fix a arbitrary prime number p, and then we want to understand the singularities of f. So we because if we only solve f to 0, then we probably get infinite many solutions. So we want to modulo prime number and try to solve the equation. So we define mi to be those tuples, so that the modulo p to the power I is 0. Okay, and then there are only finite many number solutions, because this is finite. This group is finite. Okay, and then by Chinese Riemann theorem, we know if we consider OP, then we can solve this f to 0 mod any m. Okay, and then we want to add them up and get the Poincare series, which is just adding this with this indeterminate variable, and this is called the Poincare series. Now let's look at some examples. So the first one is this f equal to x minus y squared. This cubic curve inside this two variable polynomial. And then we know this is identified to A1, right? So you can easily see this mi is just the power I, and then if you add them up, then you get this p over p minus t. Okay, let's make f a little bit more singular, and then because this cusp singularity, and then after some calculation, you can see that this pt is this rational function. So in general, Igusa proof this Poincare series is always a rational polynomial. Okay, actually, from this example we can see the more singular f is the more complicated the Poincare series. Okay, and because this is a power series, right? So from a calculus point of view, this can be understood as some integral, right? So actually, how Igusa prove this power series is rational? The method he uses is called the p-adic integral, and actually this can be specialized by so-called p-adic zeta function by using some integrals over the field Zp. Okay, so this can be seen as the antiderivative of f. Okay, so this can be seen as by using antiderivative of f to detect the singularity of f. Okay, so but the main topic of this talk is to understand singularity from classical point of view by using derivatives, taking arbitrary derivative more precisely by using D modules. Okay, so this is kind of we are going to do this from an inverse perspective. Okay. Okay. Before I recall D module theory, let's look at another motivation, which is from a topological point of view, or topological perspective. Okay. So suppose now we have a hypersurface singularity, but we are going to fix a point. So we are looking at the germ. For example, f is a polynomial function vanishing at the origin, and then we consider this inverse image of some T intersects some ball. Here B epsilon is a ball of radius epsilon around the origin, and then we pick up epsilon as small as possible, and then we take P in this punctured disk with radius delta, and then Murnau proof OMT gives us smooth fibration. So this is the fibration over this punctured disk. Okay, and then this diffeomorphism comes up MT. MT is called the Murnau fibers of F at the origin. Because the fundamental group of this is generated by 1, we denote that by T, which is a loop starting from T around the origin. And then because this is a fibration, so we know this Tx are the cohomology group of the Murnau fiber. And then a classical, this is called the monodromy action. A classical result say that the monodromy, the eigenvalues of monodromy action are roots of unity. Okay, and, but because of this construction is purely topological, we have to control this epsilon and delta, so it's usually hard to calculate. So next, we are going to we will see how we calculate by algebraic way, and more precisely by using B functions. Okay, so before I do that, let's recall some E-module theory that you may have correspondence. Okay, so in the previous fantastic talk by Professor Danilo, he mentioned a lot of E-module theories, but you are very general. I'm happy that this the material I'm gonna recall is too easy for him, so he's not covering his talk. Okay, we assume X is a smooth variety over C or more generally a compact manifold. And the OX is just the structure shift of algebraic functions or homomorphic functions. X1X is a compact manifold. All right, and then let's use Tx to denote the shift of vector fields, algebraic or homomorphic, depending on the category you are working on. And then we define Tx to be the C algebra, C subalgebra inside this very large V isomorphism of X, C linear, generated by OX and Tx. This is called the shift of maybe like finite order differential operators. For example, if our X is this n-dimensional alpha space, then this D is just this VO algebra. So this generators xi partial xi satisfy this Lie bracket relation. Okay. So this is sorry. So this is the example of differential operators, and then dx satisfies some very good properties. For example, it is non-serial and coherent. And then we can define some orders of the differential operators by setting the order of OX. The of sections of OX is order 0, and the order of vector field is 1. Okay, and then we get the order function of dx. Then we can let fp to be the differential operator of order smaller than p. And if we then do the associated theory, and then we get this. Oh, by the way, so dx is non-commutative because we have this relation given by Lie algebra, Lie bracket. But if you take GER, it becomes to be commutative. Actually, this is the algebraic quantity of the cotative model. Okay? So yeah, the cotative model. So if we have a dx module of a dx module, that means M is an O module, but instead of actions of regular functions, so we also have we can also define arbitrary order derivative on M. So that's basically what it is. Okay. And then we can take a good filtration compatible with this filtration we just mentioned, and then we can define the character variety of M. defined to be the support of the square module, because of the compatibility, the square module becomes to be a module over the GER dx. Right? So then this support is inside the cotangent module. Okay, then we have this character already satisfies this so-called Bernstein equality. So the dimension of the character value always greater than the dimension of the base space. Okay, so then the interesting case should be the case when the this inequality is a equality. Is a equality, right? So when we can define holonomic D module to be the module so that the character variety has a dimension exactly the same as the Arvin space. Okay. All right. So now let's look at some examples of holonomic D modules. Okay. Suppose X is just a one-dimensional alpha space or the complex plane. Then we can consider this M alpha, which is as O module is just generated by X at the 1 over X, which is just the localization of the structure shift at X, the coordinate upper plane. And then we introduce this symbol X to the alpha and use that to generate a dx module, because we have this because of this, although this is a symbol, but we can, by using chain rules, we can take derivative of it to then satisfy this relation. So it's a dx module. Okay. And the other one is the D module of a Dirac delta function, which is generated by one quotient by this action, the annihilator generated by X. Okay. And this module supports the origin. Okay. So then we can define regular honomicity. M is a regular holonomic if we pull back by some like a test curve, so that its pullback is generated in this K-series point of view, from K-series point of view, generated exactly by this two I call cell modules. Okay. If you so I mean this so you need to pick every small disk embedded as small as possible. Okay, zero is the Gaussian group of D modules, okay, covariant module, holonomic module. Okay. Okay, and then so Andrew talked about the solution functor, but to us we use the ROM complex, which is just a dual of the solution complex. And then for this special case, the ROM of MX is exactly this complex, but we have to use the analytic topology. Okay, so the ROM M alpha can be understood by cutting X, this alpha space, into smaller pieces. So if you restrict to the puncture disk, then it has a kernel. Sorry. This complex has a kernel, and actually we have this embedding C times X to the minus. Now X to the minus alpha is a section, is a local section. So we can embed this into this C X 1 over X, X to the alpha by X to the minus alpha, X to the minus alpha times X to the alpha. So we have to put here, right? So this is this section is here is locally constant because this one, if we use differential operator X on this, we have minus alpha, right? The eigenvalue is minus alpha, and here we have alpha, so alpha minus use product rule alpha and minus alpha to cancel each other to get 0, right? Partial Tx out that's 0, so that's why this is kernel, which is this, right? And this, because this is a multi-value function now, so it gives so if we go around the origin, the monodromy action is not trivial when alpha is not V, is not contained in D. So so we get a local system, and the monodromy function is just the e to the 2 pi times a minus. Okay. Over if we make restriction of this complex at the origin, then you can check alpha. If alpha by solving the kernel, right? This is injective. You can prove it's injective, surjective. So if alpha is not an integer, and then if alpha is something, then this is the kernel and co-kernel are both C. Okay. And yeah, so this this kind of a description make the DRAM complex can double shift. That means you cut, so that has more or less just a vector space or variation like local system. And also there's a another modular interpretation, because actually this M alpha can be, if we vary alpha, then this can be seen as the maybe the DRAM moduli, and then alpha can be, so the DRAM moduli in this case it's just a C, and then beta moduli is a C star, and then the behavior changes, right? So if we restriction to the origin, then the geometric the behavior of the DRAM, this complex changes. So we have some jump, right? So if we take exponential of this give us 1, right? If alpha is in Z, the exponential of this is 1, right? Otherwise, this is not 1, right? So if in the beta moduli, if lambda is not 1, then we have jumps, right? It is 1, then we have jumps, right? So this is kind of the jumping. This has an interpretation of jumping loci. Okay, we will use this later. We will see this later later. Okay. Okay, so in general, from this example, we see this regular Riemann request also mentioned by. So regular phonemic demodule, if you use the DRAM functor, then or solution functor, if you draw it, then we get all more precise perversities. Okay. Okay, next we're going to use a demodule to get Bernstein-Sato polynomials, and so that we can generalize the example I just showed you. All right. Okay. Now we suppose F is still now we consider this a complex situation. So F is a polynomial with complex coefficients or homomorphic function if you work in the analytic category, and then we still take X to be the with a dimensional alpha space. Then the Bernstein-Sato polynomial is a monic polynomial. We use BFS to denote it. Inside this CS, this S is exactly the independent variable we introduced to define it, so that this functional equation is satisfied. And BS times Fs equal to PS XR F to the power S plus 1. So this F is a kind of this alpha here. Okay. But here we make S varies, but here alpha is just a fixed number. So it's kind of, this is the example we mentioned before is kind of specialization of this general situation. Okay. And this PS is just a part. He said it's a variable part with coefficients in the differential. Yeah. Now let's look at some example. If F is just the one coordinate X, then it's easy, right? BFS is just S plus 1, because if you use partial X XOR this X to the power S plus 1, then by chain rule, we know the power dropped by 1, and then the power become a factor, right? This means when X is smooth, then the calculation is very easy, so the B factor is very easy. But if maybe make also, I mean F, sorry about this. If F is this like a norm function or square of the norm function, and then if you use a Laplace operator X on F to the S plus 1, then you get this. So the B function becomes S times S plus n over 2. Okay. And then if we make the singularity worse, For instance, this cusp singularity situation, then BF become to be this product of these three terms. Okay, and in this case, the not as simple as the example 4.1 and 4.2, the differential operator cannot be write down easily, so I skip that. Okay. Also, because this monic, because this CS is PID, right? All the so you can always find the monic of the distribution. Okay, so Kashwara is a great mathematician proved this like 50 years ago, more than 50 years ago, that the roots of a BFS is are all negative rational numbers, and then Kohler studied this by using from like a birational geometric point of view, and it then proved this graded roots of BFS is actually the log canonical threshold of F, whatever it is, because it's not so relevant in this talk. Okay, and then Kashwara, maybe also Margaret at the same time, they prove the roots of B functions can be used to calculate eigenvalues of monodromy actions. And actually, they proved some like a categorical equivalence between these nearby cycles for the nearby cycles along a hypersurface and the nearby cycle for D modules for regular polynomial B modules by using B filtrations. Okay, so because maybe we could go a little bit, because this definition is purely algebraic, right? And this dx as this really is discrete, right? If I draw S is still discrete, so we can easily make some program to calculate. So this theorem great result tells us how to even it's very complicated, but we can let, for instance, let the computer to calculate the roots, the eigenvalues of monodromy actions to test the singularities of hypersurface. Hypersurface. Okay. You mean this theorem? Maybe not. You have to use this like Archimedean integral to some kind of Archimedean B function or non-Archimedean B function to calculate to test when the integral blows up. Firstly, the threshold point can also be interpreted by using changeable variable formula. So, oh yeah. This implies this combine this and this, it implies the monodromy eigenvalues are user unit. Makes sense. But it does not imply collapsibility. All right. So then we want to generalize this classical picture into multivariable rings. So instead of consider the function, we can consider a polynomial function. We can consider polynomial, okay? And then we can mimic the definition of Bernstein-Sato polynomial. Then define the Bernstein-Sato ideal, because now we have more than one component, so we need to introduce a more than one variable. But we can similarly write down the functional equation, and then use the same rule to define Bernstein-Sato ideals. Okay. Oh yeah, formal. Yeah, but the actually this what? Yes. Okay. Okay. So this is what is what? or X is an. X, sorry, X is an. Yes. No. It can be arbitrary singularity. So this is for arbitrary F, capital F as well. Yep. Oh, but I mean, yes. Yeah, it divided by yeah, if you like make the both smaller. Okay. Okay, so about your job to the BFs behave similar, like this generalization of control theorem. So at least we can find element inside BF so that it is a product of this kind, so that the coefficients AI are positive, non-negative. This B is positive because I put plus here, so that means the roots are negative. So so let's look at this very seem to be very easy case. This kind of hyperplane arrangement. Then in this case, this BF has already been a little bit complicated. So it is ideal, principal ideal generated by this very long product. And so the degree here is 5, here is 3, 8, here is 3, 11, and here is 5, 16. Okay, so to prove this, it's already not very easy. You have to use the called like log derivatives, because of this actually because this is this gives us a free hyperplane arrangement, so you can use this generators of a log derivative to find the annihilated I mean the annihilator ideals inside this DX ring to calculate this. Anyway, so to the point that I'm going to emphasize is this BF in general can be calculated by computer, but usually it's hard. Okay, so so now we have this Bernstein-Sato idea that we have this in variable case, if we have just one polynomial, and then we know this Cauchy-Lagrange result that there are like the roots calculate some topological state. So we want to know if in this higher like a multi-variable case, similar state that will happen. So this so we have to find the right topological object to study. Okay. Actually, we can use Kumari topology like this case. We have this jumping when alpha is z. We have this jumping of this round complex, and we can use that to define Kumari jumping. And so suppose now we still suppose x is a variety over c. We for some technical reason we need to assume x is connected. And then we can consider this character variety, which is just the group homomorphism from the formal group of X to C star. And then we know this is just a combinatorial with the measure of the first Brady number of X. Because because C star is commutative, is a bigger group. Sorry. And then MX has some modular interpretation in this parameterized order C star representation of P1X because like then C star representation. This is the G star or C star or GR1. This by the Riemann-Hopper correspondence, every representation of P1 is just a local system. So MX has some parameterize those two states. And then we can define inside MX this cohomology happening loci. by requiring by taking the homology, and if it's let's look generic vanishing to they must be vanishing generically. So it's a proper subset. Okay. And then Greeley's field, Simpson at B1, which is also one closer of this result. So that this Japilosa SX is a finite union of the torsion translated subtoric. This is very similar to the monodromy conjecture. Right? This is actually a generalization of the monodromy theorem. Right? So torsion translated means in one-dimensional case it's just the roots of unity in system. Okay, now we want to study this in our situation, specialized to this our situation, because in our situation, this functional to divide BF is kind of can be specialized, right? So we can take a germ, and then the functional is still hold. That means this B function should contain every local information as well, right? So that means we should, instead of consider this Japilos like globally, we have to consider this local Japilos. That means we need to detect this non-vanishing or every small neighborhood. So this gives us a local Japilos. Okay, and then if n is if n and r are the same, and then this polynomial map is identity map. And then SF is just a opinion of all coordinate subtorics. Actually, the example we are looking at the very beginning is actually just the case when R at n equal to 1. Okay? And if capital F degenerate to some polynomial, and then SF is just then we can still define this local Japilos, but this is nothing but the eigenvalues of the monodromy action on monofibers or monofiber comods. Okay, so this SF, this capital SF is exactly generalization of this lower SF. So this we can believe this is the right analog on the right hand side to compare with the BF. Okay. Oh yeah, then Voodoo Wang, Liu Samuel several years ago proved that this SF also satisfies a similar this torsion translated problem. This algebraic problem. Okay. Next is our main result. Okay. So like more than 2 years ago, our brother Voodoo conjectured this SF should be the right analog of S lowercase f, so that the zero locus of the Bernstein-Sato ideal, if you take an exponential map, you actually recover SF. Here, because I didn't use the character, I don't use the character variety notation. This is actually MCR, so which is just a cover chloride of the dimension R. And here, because we have R many, the polynomial map has R many components. So BF has R introduced variables. So the spectrum of that is CN. So we have this universal covering map. And then we have this relation. Okay. Actually, our main result is the proof of this conjecture. Okay, without any condition. All right. Any questions so far? Oh, you mean here? So this is just jumping on top. We detect the local system in the moduli space. Yeah, if locally jumps along D, then we marked it, and we code it, and then we union them together. All right. So the method we use to prove this is kind of a combination of other studying D module from a relative perspective and a logarithmic perspective. So because of time reason, I cannot go more details. But I'm happy if you are interested. I'm happy to discuss that with you. Okay. So finally, let me give some remarks of our result at some of my thinkings about future directions question. Great. So recently, our May theorem has been generalized by myself to a equivalence between D module nearby cycles for this capital F and the so-called sub-R specialization complex. This is sub-R specialization complex is complexes are natural generalizations of the linear cycles for conjugable sheaves or perverse sheaves. And the equivalence is induced by equivariant Durand function. So because in the previous test we can see here this SF and the BF are related by this exponential map. So at shift level, the shift we need to consider should live in different having space, right? One is X times this CR, the other one is X times this C star. But those two are related by this universal covering map action. So so you probably can imagine if you want to get this is also this result is also like generalization of this control wedge result, because they also construct nearby cycles for D modules along one polynomials, and then the link constructed the nearby cycles for along that type of surface of the polynomial. And then this result tells us we can do this for more than one. I mean, it can be made into the equivalence of that, but it's kind of a factorial comparison. I mean, yeah, you can consider if you have a D module here or regular polynomial D module here, then we can construct the nearby cycles of that module along zero locus of F via multivariate way. And then if we take, then we can construct some nearby cycles for those. And then if we take equivariant Durand of that nearby cycle, and then we get this sub-R specialization complex. Okay. By the way, I forgot to mention. So this SF has another interpretation, which is the relative support of the sub-R specialization complex. All right. So so by this result and our main result, this story at the oh actually this the nearby cycle are relative D modules. So if you have a relative D modules, then it has some like a relative support, right? So it has support, and this support is exactly as it's exactly zero locus of BF. And this side is kind of a this is sub-R specialization is a I mean is a controllable shift over C K1 X minus B maybe C star R. So if we take spectrum of this, gives the support of sub-R specialization. So So this support is exactly SF. That's the other like geometry interpretation of SF. So if they are related by this equivariant way, so that means exponential. If you take a sorry, I'm really sorry. So if those two categories are the same, so the support modulo the universal covering action must be the same. So this is why it is. This side, this side, this side specialized to body verification. Okay, so that means this means the merit result means at the level of Riemann or Brooks balance at the nearby cycle, the story is over. Oh, I think myself this. Yeah. But the whole story is far from being over because I mentioned some arithmetic perspectives to understand singularities, what I did without further uh, interpretations. Now let me fill that gap up. Okay. So first, we know so our tells how do we understand the zero locus of both axonal ideals after take exponential. So how about the because the BF is the ideal inside this CS1.SR. What if we use we look at the scheme defined by the ideal? Okay, and then there are some like geometry of it too, right? So we do make some conjectures about the whole or the component of this scheme given by BF should be. So more precisely, he conjectured that every irreducible component of a BF must be some translated linear subspace of CR. True. So okay. And this is like as far as I know, this conjecture is what we have some statistic of it, but I don't know how to prove it. This is kind of a because from here, we know because that means this d-module nearby cycles, the support relative support should be because this is equivariant functor. So if we pull it back, then we get this pull it back of SF give us the relative support, right? But BF is kind of a cut from because from the universal coverage is not 1 to 1, right? It's like Z to 1 or ZR to 1, right? So we don't know we don't know where we should pick. We should pick like a lattices, right? This ZR is kind of a group, right? We need to pick the BF can only see lattice information, but where the lattice stop is kind of mysterious. This is kind of contained inside BF. Okay, so this is one conjectures remain open. Okay, the second one is how do we get arithmetic information from this about the information about F? So you know from the very beginning of this talk, we divide this Poincare series. And for cusp singularity, we know we get this poles like the poles of the Poincare series are like T minus T. This is similar to S minus plus 1, and the other one is P to the 5th minus plus T to the 6th. This is corresponding to the roots S plus 5 over 6. Okay, so that means as I said, the D module. I mean the D module is kind of taking derivative, right? But the arithmetic information Poincare series is kind of taking integrals, so they should be inverse to each other. So conjecturally, this arithmetic information can captured by this topological information. And this is called the weak monodromy conductor. The more generally, because of the Kashwara malware result or our result here or the main result, we know this topological information and algebraic information could be equivalent. I mean, we know how they related in some tests. So another question is how can we get the arithmetic information from algebraic for both f and the capital F? This is called the strong monodromy conductor. And our main result implies that the strong one implies weak one. Okay, this is the last remark I want to make. Give me one more minute, and I want to make the last remark, which is improving this theorem at the main theorem. Actually, our proof motivates us to study log modules. Okay, and we probably need to understand the log Riemann-Hilbert postulate better, so that we probably can use log to construct a log perverse log, like the double shift log perverse shift log Riemann-Hilbert postulate, so that we can make a bridge to connect these two parts or these two parts. And this is what we are doing now. I think I'm going to stop here. Thanks.
Elementary question. What do you mean by a log D module?
Oh, actually, this is a very nice question. So, let's go back to the definition of Bernstein-Sato polynomials. Okay. So this S here actually is not completely arbitrary. It's not. It has some log interpretation. Actually, this S is just the log vector field. So by using graph embedding, actually given by F, so this S. So we have this log structure of the divisor F equal to 0, and that S is exactly the direction, the log vector field direction. So that's why it's natural. Actually, this B function C give us precisely why there should be a log Riemann-Hilbert as well.
Maybe it's a very naive question, but your first slide was about motivation from arithmetics. Could you please explain one more time what is the connection of arithmetics and the rest of the talk?
Oh yeah. So I'm sorry I didn't make that part very clear. So actually, this Poincaré theory can be specialized by the so-called Igusa Kelly zeta function. So to construct the Igusa Kelly zeta function, you need to use some higher measure. Actually, this is kind of the Igusa zeta function is the to me I understand it as the mailing transform of OX of C or along F with respect to the higher measure. So it's an interval. But if from an arithmetic point of view, okay. But D module kind of doing this opposite. We take derivatives. So this philosophy is like this D module, this dxs times fs can be understood also. So this fs is similar to the factor inside the classical Mannering transform. So this C can also be understood as some kind of a Mannering transform. So the philosophy is those kind of Mannering transforms to be maybe at least has some relations. That's kind of the philosophy behind monodromy invariance, to me, at least.
Is there no more question?
Well, since this is the last talk, can you explain a little bit more about the proof of your main theorem or its generalization?
Okay. So first, so first we consider this module. Let's look at the definition. Okay. So first we consider this mod S1. Let's use the two variable for instance. And then we have F1, S1, S2 here. And then this S1, S2 are variables, right? And then we want to specialize this. So these are CS modules. So we pick M to be a maximal ideal of some alpha inside C2. Okay? And then we localize, we take specialization of this, and then for some special alpha, and then this module, and we can take a derived tensor over this C, this one, this two, and then this module, we then can give us L lambda. And then we compare this, we do the same thing. S1, S2, F1, S1, S2, S1, SL. With respect to the same segment, okay? And then if those two are different, then almost it's the same as this comargin not zero. So kind of and this quotient, this part not zero exactly almost the same means this quotient is not zero. Kind of specialization. So that's why it will be almost the same. But we have to module this Z action, the universal deck transformation. Basically, that's the idea.
I think the talk is over. Thank the speaker.